All right, hey everybody. So today I want to talk about an important but somewhat technical topic, and that is a question about how to take a differential of a function between two surfaces. First, what exactly do I mean by that? Right? Well, recall the idea of a differential was introduced in Calculus 3, and it was introduced back earlier in this video series as a way to record first derivative information about a complicated function, right? So specifically, a differential, so if you're given a function f, right, then a differential is a way to record a lot of information about the first derivative or different first derivatives, different first partial derivatives of our function. And the way that we've seen this most classically is if we have a function from Rn to Rm, then we can encode the differential as a matrix, specifically a matrix of first partial derivatives of an appropriate size. So if f is a function from Rn to Rm, then this would be a m by n matrix, right? And each row in the matrix would correspond to a gradient, to use a little bit of Calc 3 language. So we would end up with this. Let's do an example, right? So if we had a function, let's just say f of u comma v equals u comma v comma u squared plus v squared. Right? This could be thought of, I should say, this is a parameterization of a surface, right? So we've seen examples like this before. This could also be thought of as a function that's mapping R2 into R3. And so the end result would be a 3 by 2 matrix for our differential, and we would denote this as df in its matrix form is given as the 3 by 2 matrix in which each row corresponds to one of these three entries, and each column corresponds to a given kind of derivative, right? So this first row would just be looking at the u function, and we would take its gradient. First its u derivative, and then its v derivative. So the first entry, I think in general, we would call this, if I called this x, y, and z, then this would be dx du, or partial x partial u, partial x partial v. And then similarly, we would get partial y partial u, partial y partial v, and then partial zu, partial z v. And if we want to skip ahead and actually fill in those entries, in this case, the entries would be 1, 0, 0, 1, and then 2u, 2v. And that's encoding all of that first derivative information about this function. So if we're thinking of the differential as a function or as a way to encode all of this first derivative information of another function, this was a function from Rn to Rm. What if I want to have a function between two surfaces? Does it make sense to talk about a differential of such a function? It turns out the answer is yes, but especially here at the beginning, our conversation of how to compute such an expression, or what it even really means, will be a little technical and a little complicated. But there's good reason to talk about this now. We just saw a quintessential example of a function between two surfaces, and that was our function, the Gauss map. So recall, right, our Gauss map was a function from one surface S to another surface, specifically the unit sphere, and we defined it as we would take our point P, right? So if we had a point P down here, what we would do is we would compute the unit normal vector, n, and then we would point out where that unit normal vector was on this sphere. So this unit normal vector is pointing up in this direction, so that would correspond to this point on the sphere. So this might be my point P, and this might be my point n of P. And there's this question of, if I have this if I have this Gauss map, how can I define, or does it make sense to define a differential of this Gauss map? So again, it turns out that the answer is yes, but first of all, specifically, the differential will be a map that depends on each specific point P. So when I talk about the differential, I'm going to be talking about the differential of the Gauss map at the point P. Secondly, this will be a function not from S to S2, but the differential will be a function from the tangent space at P on the surface S to the tangent space at n of P on the surface S2. In other words, I'm going to be thinking of this as a function that maps this tangent space to this tangent space, right? And so that's important because each tangent space can be thought of as itself a set of Rn. In this case, right, this tangent space is like a tangent plane, and it can be thought of as R2 by itself. It can be thought of as the set R2. Similarly, this tangent space can be thought of as a copy of R2. And so this map is starting to look like a function from Rn to Rn, specifically from this copy of R2 onto this copy of R2. Now, that being said, how do we actually go about defining this? Well, this definition will take place, or we will be able to compute such an expression by following the rather complicated set of steps below. So to define this differential, we're going to do the following. First, we are going to pick a parameterization for our surface. Right, so this was our map n. I guess here, let's make this a little smaller so we can see all of this at once. There we go. So this was our map n. Let's go ahead and define a parameterization. That is, let's define a map x from this set here, right? So this is our set U, and x is a parameterization of our surface S. So x is a map from U to S, and there is a corresponding map that we saw last time, right? Capital N, which is just the composition, slide down just a tiny bit, the composition of both of these maps. So we had this function here, right? That was n of x, which we called capital N. So we have our capital N mapping our coordinate system all the way over here to the sphere. We also have our original parameterization x mapping this coordinate system to the surface S. From there, we are going to look at a curve, alpha of t, in our system over here. And we're going to specifically focus on a point Q, which I realize I should define here, that maps to this point P. So let's say we have our corresponding point Q, and Q maps to P, which then maps to n of P over here. So with that as our setup, we are going to look at a parameterized curve, alpha, that's over here, right? And so maybe this is my curve alpha. And alpha is designed in such a way that alpha of 0 at time 0 is equal to Q. So maybe this goes from time -1 up to time 1, and at time 0, we're passing through the point Q in question. Now, because of alpha's definition, right, it's a curve defined inside my domain U, I can see its image on this picture and also its image on this picture. So x of alpha is going to be some curve like this, maybe. And then maybe it goes sort of behind our picture up to there. So maybe this is my x of alpha. And similarly, I have an capital N of alpha, and that might be the curve that sort of goes through like that, right? So there's my alpha curve, the corresponding image x of alpha, and capital N of alpha. All right. So now we can have a little bit of fun. We can compute the derivative of x of alpha at the time t equals 0, right? So I can take x of alpha, that's my curve in this picture. When I compute its derivative, I get tangent vectors, right? And when I compute its derivative at time 0, I get a tangent vector, which we call v, and that is lying in my tangent plane. So let me, I'm going to use light green for this. My tangent vector v is maybe this vector right here, and that's my vector v. So I calculate my tangent vector v, not necessarily a unit tangent vector, right, but tangent vector v. I can similarly calculate a tangent vector w in this picture. So I calculate the derivative of n of alpha at time 0, and I get my vector w up here. So I've got a vector v, I've got a vector w, and then we define the differential as follows. We say that the differential of this Gauss map of the vector v is equal to w. So our map is defined in this really complicated way, in which if I want to figure out what dn sub p of v is, I have to construct this curve alpha that gives us vector v in this picture, and I see what the corresponding w, the corresponding vector in this picture is. And I say that dn of v is equal to w. So that is super complicated and very technical. But since it's mapping vectors in this R2 space to vectors in this R2 space, it will give us information on how this Gauss map is behaving, especially in terms of some first derivative information, right? Because we're taking some derivatives of these here. So we're getting a sense about how tangent vectors get mapped to other tangent vectors. Now, our original differential, right, our Calc 3 differential, we were able to compute as a matrix of partial derivatives. And there's a question of, will we find easier ways to compute this? And the answer is yes, we will. But in the short term, no, we won't. But that's okay. We actually won't do this whole lengthy process out by hand terribly often. I want to conclude this video by looking at two important images of two important vectors under this differential map. Right? So specifically, I have my setup here. I have my Gauss map n. I've picked a parameterization x. I've got the corresponding n. And what I want to do is I want to consider two specific curves for my alpha of t. Right? And so the first example is I just want alpha of t to be the curve t, comma, whoops, I guess I should specify. So this should be, if this is my point that I'm interested in, let's say that this is the point u sub 0, this is the height v sub 0. And so I really want my curve to be the curve t plus u sub 0, comma, v sub 0. In other words, it is exactly the coordinate curve, the u coordinate curve for this point, lined up so that at time 0, I'm at the point I'm interested in, right? It's the u coordinate curve in that I'm just getting this flat line right here. And I've chosen it so that it's passing through the point I care about at the right time. Now, from things that we've already seen in previous videos, if I go and I map this alpha into my x space, right? So I take x of alpha, I'll get some curve here, right? I'll get a curve there, and then I take the derivative at 0, and I'll get a vector. But what makes this important, what makes this an interesting curve to choose, is that at that moment in time, my vector is exactly the vector x sub u, right? If I take the derivative of my coordinate curve in the image, I get this all-important vector x sub u, right? That partial derivative of x with respect to u. So I get x sub u at the appropriate moment in time, right? But I can do the same thing for n, right? If I have my vector n, I have my map n that's mapping over to this space, I can take the composition n of alpha. I'll get a coordinate curve down here, right? So there's my coordinate curve for this map. And if I take the derivative at 0, I will get a map over here. I'll get a vector in this tangent space. And this vector will just be n sub u, right? Because my map n is really not that different than my map x. They're both parameterizations of their given surfaces. And so the coordinate curve, right, the one that we're looking at over here, should give me the partial derivative of the parameterization with respect to u and the partial derivative of the parameterization with respect to u in both cases, right? But what we've proven, and I'll switch to a darker color just to make sure it's visible. What we have proven is that if we go to take the differential of our n at the point x sub u, right, so at the vector x sub u here, the end result is n sub u. And similarly, I won't draw it out, but you can imagine similarly, if I go to take the differential of the vector x sub v, the end result will be n sub v. Right? So even though we don't have a great way of calculating the differential at the moment, these two identities are really, really good to know, and we'll use them in what's to come. The very final thing that I want to say in this video before I close is, in addition to having these identities here, we have our overall, here's what I want to say. In addition to having these identities, I have this really slick observation that I sometimes like to make. And this comes back to an observation we made in a previous video that said this plane right here, right, the tangent plane at point P, is identical to, or parallel to, the tangent plane of this picture at point N of P. So we often like to identify this tangent plane with this tangent plane. And so there will be moments, if I go all the way back to, too far. If I go all the way back to this screen and slide up, right, we have this formula, or I should say maybe like this schematic that we like to look at, in which we have this differential is a function from TPS to T sub NP of S2. There will be moments in time when I want to recall that these two tangent spaces are actually parallel to each other. And so there will be moments when I might want to pretend that this tangent space, by virtue of being parallel to TPS, is really nothing more than TPS. And so there will be times when I want to look at this as a function from this tangent plane to itself. And I'll try to, again, identify those moments as they come up. But there's a nice little, there's some things that we can get away with by thinking in these terms. So that is this very technical but ultimately important idea of taking the differential between two surfaces.